Whenever it's yeah.
Okay, let's wait for one more minute, and hopefully more folks coming. I noticed the number of attendance dropped quite a bit today. I hope it's due to the cold weather. But let's wait for one more minute and then get started. All right, let's get started. So if you haven't found a seat yet, please find a place to sit down. There are a lot of space available today, so don't be shy to sit in the front as well. Cool. So today we're going to talk about the memory mapped I/O, MMIO, and the APB buses, the advanced peripheral buses that we're going to be mainly used in a lot of the labs and also later on in your final projects. Some quick announcement. The homework 2 is posted and it's going to be due this Friday. And the office hour is changed to Wednesday 11 a.m. to 12 p.m., currently at EECS 3217. I will be updating this office number once I have my permanent location. But for now, this is the time and location. The time will be fixed. And starting this week, you will be starting on the lab 2. And from this point and on, the pre-labs are going to be due before your lab section starts. Yes, already questions? Okay, yeah.
Is that true for pre-lab 2 as well?
It is, yeah, that's especially true for the pre-lab 2. It's due before your lab section starts. Okay. All right, so component of the day. Today we're going to talk a little bit about the voltage regulator. It's kind of built on top of the battery we talked about last time. So we talk about how they are a little bit, the whole curve, the output voltage can be varies at the different state of how much it is charged, right? So how do we deal with it? So it turns out there's this very, very convenient component called a voltage regulator. It's basically the electronic component that maintains or tries to maintain a constant output voltage, regardless of the changes of the input voltage or like the load conditions. And it kind of ensures the stable power supply to the electronic devices and circuits, protecting from like over voltage, under voltage, and also some of the fluctuations in the power supply if that occurs. Yes.
Is that like the same as a buck converter?
I think functional-wise, yeah. Yeah. There are also different types of the voltage regulator as well. There are like fixed ones and also adjustable ones. Fixed ones basically give you like a fixed like maintained voltage, and the adjustable ones, you're able to tune what's the actual voltage you're trying to maintain with like some extra passive components like resistors, etc. And yeah, these when choosing these ones, basically make sure that the first you know the type, is it fixed or adjustable, and then also what's the current rating, meaning how much current it is allowing you to draw out of it before it can still maintain that voltage. Yeah, and also the input range of this regulator. You don't want your input range of whatever battery you're using be extending the input range of your regulator. Otherwise, you will not be able to perform correctly. Yeah, a little bit on last lectures. I think some of the folks asked about the space directives. So basically, that dot space and A, that means reserve a byte of the uninitialized memory at the beginning. So if we assume this whole program start at like memory 00000, which is usually the case if it's fully boot up on the embedded system, then it basically means the first a byte of data is being reserved with not much, well, with no data in them, and then the data, which is the bottom four bytes, is going to be put at the address of the 0008. So yeah, hope that clears out any of the questions from last lecture. And today we're going to talk about these three things. Basically, the first, the memory mapped in and out, MMIO, and then the second, we're going to talk about the bus architectures. These are basically how the data got pushed and transferred around the chip. And then the third, we're going to talk about the specific bus structure that we're using in our class, which is the APB. Hope you still remember this from previous lectures. It's the advanced peripheral buses. And yeah, this is like, you're going to see this over and over during the class, but basically this is the simplified version of the Cortex M4 architectures we're using in class and also in your lab. And this is what the memory maps of the Cortex M4. So they have a bunch of stuff inside. They have so basically among these memories, remember like in total we have about 4 GB of the address available, just based on the 32-bit of the address that's being allocated to the 32 bits of the buses. So these spaces are pre-allocated for different vendors to use with certain amount of memory. For example, if you look from like bottom to top, the code part, which take about like 0.5 GB, it's the on-chip flash memory for like code, and the SRAM is basically for the a lot of the where the data was stored. Like for example, last lecture we talked about like the stack and heap, where all those register values sometimes got stored there. And then we have the peripherals, which is what we're going to talk about today, mainly actually. And then we also have some external ones. The external RAM, if you do choose to connect one, these are not on the chip, and also the external devices, such as like SD card or etc. So you'll notice that although they kind of go everywhere on the chip, and then some of them are not even connected to the chip for most of the time, but they're all being accessed through this, or they are all mapped the same in this whole memory in and out system, so that the chip from the core, like the core's perspective, all these things are equilibrium to them. They just use the same amount, same command, and then to do the same operation. It's just the address that will be determined where these data actually go to, and any other additional processes needed for making sure these data are available when they were caught, or the spaces are available when it's being stored. Yeah, and I can show you a little bit on how they goes on the whole system. So, like we said, basically everywhere. And the little bit something to notice here is the two external stuff, the external RAM and also the external devices. So technically they are not exactly on the bus, but once they're connected, they go through these buses to transfer the data. So we just put it in there as like a reference. Yeah, and as we just briefly talked about before, because since it's everywhere, and the only differentiator or identifier of them are the address of the address of their locations on the memory map. So these are all the different locations on the chip that, for example, the store or like load function can access. So how do they know exactly where to access that? Which is what we're going to find out today. Obviously, hence the particular devices. The particular addresses is going to be the key here. But there is also a few other things. All good so far? This hopefully is pretty straightforward so far. Okay. So right now we're going to specifically look at the peripherals, or like the GPIO peripherals as an example. You guys have been playing with these with like the LEDs in lab. These they are basically addresses allocated to each of the GPIO channel, and then each of the GPIO are given exactly 1 kilobyte worth of space, and then they are all kind of represented by like a binary number, and then as you probably will imagine, all those numbers are held, or like all the data are held by the bunch of like D flip-flops to hold the state of what's the current inside of each of the GPIO. And a little bit, like basic ideas of the memory map that I know and why do we use that. They are different alternatives to this type of structure. For example, what they call the port mapped in and out, which is was usually used for for more general computers. For example, the Intel x86, they use like separate address space for each of the in and out devices. And as compared to our case, everything is treated the same as memory location. And for those like port mapped in and out structures, they would need like special instructions that's used to access these in and out ports. Remember, like when you go to your terminal, you open like div, and then you will see a bunch of names there. Those are the addresses space that specifically assigned for those ports. And on the other hand, the MMIO, which is what we're using on our microcontroller, is basically a simpler but more convenient way to interface with the I/O device, because it essentially treats everything the same. So you can use the same set of instruction set, same set of essentially same program to interact with them, and then you doesn't necessarily have to worry too much about the differences or handling external in and out ports, etc. Of course, there comes like some drawbacks. It's basically a little bit lower performance, but in the end, the trade-off became, on the other end, it's easier to implement. For example, this one quick store effect, the quick store instruction happens. So basically, the core stored into some memory address. The core doesn't really know where this is going to go to. It just assigns the correct or where the memory address is supposed to go to. And then the system basically figures out, based on the address, it turns out to be one of the GPIO output registers. So then that value got signed onto the GPIO output register, and then that data, the digital high or lows, became like the output into the physical world via the GPIO pins on chip. And we can also look at like a slightly different example away from the peripherals. So for example, some external devices like the SD card, it uses the load and store instructions, like generic ones from the core. And then the goal here is to be able to interact it like just as if it's a part of memory, but also miniaturize the on-chip memory. Otherwise, it kind of doesn't make sense to have such external devices here. So how do you think they're going to design the interface between them? I can give you a little bit hint. They did not build one register for each of the 4 bytes on the SD card. That would be quite stupid. That basically you put like 1 gigabyte worth of registers to map directly onto 1 gigabyte worth of external memory. So how would you design this if we have now that we know the address and then we know this is by looking at the address we know this is part of the external memory or external device. How would you design that little interface in between to make sure the core still have the access to the whole SD card memory, but also meanwhile it doesn't cause a lot of extra hardwares, registers, or any other things. You can think for this for like, I don't know, 20 seconds or something, and then if you have an answer, please raise your hand. Okay, any ideas? How would you design this interface, kind of interface system that interact with our peripheral buses? Yes?
I don't know if this would work, but would you assign like the number of addresses proportional to the storage of the SD card and then just like have continuous
Sorry, do you mean like we have the same amount of memory address assigned in this interface, and then, but how do you deal with the data? Do you have something to, like, does each of the address points to a register or points to a piece of, I guess in this way, a bunch of D flip-flops or other hardwares to store data, or how do you deal with the data coming now that you have the address? But I think so you're on the right track. Any other guesses? So basically, there's some way to miniaturize the amount of address we have here, and then somehow also get the data to the correct location. Yes?
So I don't know if this is what Eric's doing. I have like a big chunk of memory that just has all of the data that you're storing to it, and then each entry you put into it, you have a register with like, I don't know, some sort of header bit, and then like address where you have to like index to. That way you only have X amount of entries as registers rather than like 1 gigabyte worth of registers.
So you're saying we have some kind of like flag systems that identify if the incoming data based on the address is going to the SD card, and then we kind of propagate that data to it. Is that what you're suggesting? See, yeah, I think that's pretty much the right idea to go forward. And they might implement it slightly differently, but basically the idea is the same. So it turns out that they did like a state machine, like a finite state machine. Basically, at all the time, it look at the addresses of all these instructions to see if these command or these instructions is talking to me. And if it is, then it push the data here, and then just push that to the SD card. So essentially, it's like you can think of it as 1 gigabyte of virtual addresses that's being handled by this state machine. And how it works is, like, for example, you only need like a couple registers. For example, the state machine would check the address, and then you have like that one buffer register. If it is, for that address, it just take that data into that buffer register and then push that data to the correct location on the SD card. So like that one state machine plus a couple buffer registers will be able to give your full access to the entire 1 gigabyte worth of the SD card. Pretty clever, right? Okay, so the quick review of the MMIO, hopefully it's like a pretty straightforward mapping so far. Basically, it's like a method for interacting with different like peripherals and other elements with the core. SRAM, the flash, also different types of the external devices, etc. And all those stuff, including like peripherals and external devices, are represented just like memories, just like SRAM and flash. And then they will be basically the core will be using the same instructions to access the entire memory, MMIO map, the store and load. And there are like some basic types here. So the first one is like we talked inside of the peripherals, like GPIOs, etc. They have the actual hardware registers that's assigned at each of the given address. And then the second basic type is where we just look at basically have the state, like a state machine that's being state machine interface that acts kind of like a virtual registers for the external device or external like memories it's being connected to, like SD card. And at the end of the day, this is what's important. These are all just loads and stores, and then you will be able to like read the data sheet and learn how to config and use each of these peripherals. But yeah, at the end of the day, they're basically part of the memory. You can think of them as part of memory, and then you interact with them just the same as the rest part of the SRAM or flash. Oh, by the way, it's worth noticing that all those registers, like the core register or process registers, we said it before, like the 16 registers as well as 5 special registers, they're not part of this memory in our system. They're part of the core itself for like the immediate calculations, etc. All right, let's go to the next part, and then it's going to be the bus architectures. So a data bus is essentially a set of wires, and then it supports like circuit and protocols, communication protocols, that provides transportation of data between two locations on the core or from the core to the outside physical world. And there are different types of, well, there are mainly two types of interference, the two types of the buses. One is the parallel, and one of the is the serial. So the parallel one is essentially a bunch of D flip-flops wired directly to each other. It's much faster, but in the trade-off, it's going to be needs more space. And those things are usually used for like the on-chip communications. And the serial ones on the right, it's basically it sends a bunch of high and lows over time, and then the good thing of it is it's only using one physical wires to do that. And it's usually used for like off-chip communications like I2C, I2C, or like SPI. That lets you talk chip to chip, or like from the core to other peripherals devices that's connected to the chip. And for this part of the lecture, we will mainly talk about the high-performance buses, like essentially the parallel buses on the left. But just a side question, does anyone know why like we usually use on-chip as parallel communication and then off-chip or between chip as the serial interface? Any guesses? Yes?
Because we want to have communication on chip done faster.
Yeah, that is a very good point. Any other thoughts? So that solves why we want parallel on the chip, but why also we usually do serial for the off the chip. Any guesses? Yes. Allows more output from the chip. You mean like given a set amount of hardware, we're able to output more? Is that roughly? Yes, that's basically the idea. So on the one like chip-to-chip communications, they are also always almost always have these limitations on the space we're going to do. The connectors take space, and so usually on the outside, we just do serial ones with limited amount of pings. And also, chances are these things do not require a lot of super fast communications as well. And for the on-chip ones, the reason we're able to do that is because it's so compact, and then the parallel wiring inside of the chip is actually much easier to do, and because they're so much smaller, like the connecting point. And this is like a photo of the A008 microprocessor, and then let me just show you what are the, you have all these like normal stuff you would imagine, all those instruction registers, the LU, computation unit, the registers of, and like the PC, the program counter, as well as the stack. Everything that we covered so far, well, most of it. And then these are the actual buses that's being color-coded. So the red and blue ones are the power, so power bus that goes, as you would expect, around the whole chip. And that another thing you might not be expecting is that all those rainbow-colored are the parallel data buses, that they also go around the chip. It kind of goes to everywhere. And the reason for that is, and the reason, which is the reason why we need to have all those bus communications, bus architectures, is because we need to, a lot of components on chip, even on chip, it's pretty far away from each other and kind of all over the place. So we need those parallel high-speed communications to, connect them all together with the data sharing and data transportation. And this is like a Felsted parallel bus example. Basically, it's like a counter. I can show you probably with, and let me show you how it does. So, yeah, we have the link to the website. You can access it just like just by copying the link on the slides. So basically, what it does is it increases 1 bit, one value over one cycle, and then just keep on, keep on going. And every time when the clock became positive, like the positive, the edge happens, all those values got updated along all the flip-flops. And usually they have like a reset, so if I reset it, then nothing happens, and if I, disable the reset, basically asking it back to the calculation. And then it's gonna be doing the exact same thing over again, basically counting 1 bit up every time. Yeah, just figure something interesting to show. But in case you want to know more about how they works, this is the website. It's very long, but you have access to the slides. So you just copy it into any browser and play around with it. So that's one of the quick examples we give you. They are also, but there are different types of peripherals, and how are we able to send data to any of the individual peripherals? And what signal lines that you might or might not need, you might need in order to have besides the data wire, which is what you need where you store the data that's being loaded or stored, and the clock signal, which is what kind of keep the entire system alive during the update. So basically, yeah, you can work together on this and discuss what are the other signal lines that would be needed in order to have this whole system work. So we have the different addresses assigned to different part of the memory mapped IOs. For the peripherals, even for the peripherals, there are different types of peripherals. There are GPLs, there are other different peripheral devices that connects to it. How we make sure that the data was delivered or stored or loaded from and to the correct peripherals. Any other signal we need besides just the data line and the clock line. Talk to your neighbors. All right, any thoughts? Any thoughts so far? Besides the data and clock, any other signals that can be helpful in order to make sure the data is going to the correct place? Yes?
Serial buses like SPY, you need to plug SPY as well, so you can tell which device on that bus gets the data you're sending.
For the serial ones? I think for both parallel and serial, you would need some sort of, yeah, that is correct. Any other thoughts? A chip select signal that you know whether this specific peripheral is being enabled to or being active to respond to any of the signal on the bus. Any other thoughts? We probably need the address, right? The address signal is probably needed for all those peripherals in order to at least determine whether it's calling me or not. Okay. Yeah, we can probably look at it together. So we will call these requesters and completers. Requesters is basically who sends out the instruction, and the completer is, in this case, peripherals that's being, the response or being called to do any of the specific instructions. So there's going to be data pings, like the data signal, and then the address signal, which you probably you would imagine probably somewhere there. The clock that's shared with the other components, so that everything's synced, and also a bunch of the control lines. And yeah, and those things, some of them will be connected to another device or like another parallel completers, and some of them will be just individual ones. And let's talk a little bit more on the control lines. So basically the control lines are like additional dedicated signal that manage and coordinates the data transfer between devices. And they do not carry the actual data. Instead, they provide some other critical informations like the selection, like the select pings, as well as some other operational signals necessary for the successful communication, like other flags or ready, etc. And yeah. So yeah, flag ready. Oh, and also they contain, for example, the read and write pings as well. So it will be able to know whether this operation is actually asking me to do a read or write to a specific a memory address. And some of the terminology, I should probably put this one slide earlier. But basically, transition happen between a requester and a completer. Sometimes they call initiator or target. They're essentially the same thing. Requester or initiator, it's what starts the transaction event and controls which direction devices should be receiving and transmit data. And sometimes they're also referred as master. And the completer or target device, they can only transmit whenever the command is being sent by the requester, and that's being targeted to that one completer. And sometimes the old terminology, they call these a slave device. So like a master device and a slave device. And they usually share a lot of resources. Some of the differences are when not using a bus. Like why are they? Although they share a bunch of resources, the completer will not do anything essentially, not transmit any of the data unless it's being called upon. This is because we're trying to make sure there's no bus collisions if multiple things are talking at the same time. So on the completers, it's always active, only active when it's being called upon. Otherwise, it stays silent, even if there's data going around the bus. So in order to do that, there's this thing called tri-state drivers. You don't have to know too much about this, but basically it's like a way to make the completer electrically disconnected from the bus. it's called like a high impedance or high Z state, and so that it does not have any chance to collide with any other data. And some, as we mentioned in the previous slides here, so some of these are shared, some of these signal lines are shared, some of them are individual ones. And we will talk a little bit more in detail on that one as well. So how do we use buses? Basically, on the core, it sends out a command, either store or load, in this case store, and then on the requester, it kind of goes through sometimes state machine and decide what to put inside of this inside of these buses, and check if the address is in the range, which type of command it is, load or store in this case, and what are the other control bus signals, like the target address and other like control lines, and of course the actual data itself. And from the completer side, it's basically it will look at the control signals, and if it's load and store, and if it's calling me, and if it is, then what should I do essentially? And we will learn in the next few slides on the specific bus structures we'll be using, which is the APB, and then that will tell us more details on what exactly what are all those signals are doing, and which ones are shared between the buses, shared between the peripherals, and which ones are individually assigned to them. Which is exactly here. So this is the ARM APB Lite, which is the thing that we're using on our on your chip. That's the ARM Advanced Peripheral Light Bus. And a quick recap from before. Basically, we have two types of buses here, like one high performance bus, AHB, and one advanced peripheral buses. The APB, which is the one we're going to be mainly talk about on the right, it's a bit slower and simpler. It's usually used for communication with the peripherals, for example, interacting with humans, like one human typing some like make a switch change, or like some press a button, etc. And this is because we're like practically very slow, like sloths in the eyes of the core, because the cores usually run the clock at a few hundred megahertz. So any of the human interaction will usually be considered pretty slow, and those are what the APB are mainly working with. We're not going to talk too much about the AHB in this class, but basically it does similar things, but it's like faster and more time critical. It's like a more advanced version of the peripheral buses, but the underlying logic is pretty much the same. Yeah, so that's the part we're going to be mainly talk about, the APB buses. Some useful resource, if happens to be interested, they are the whole menu on this. It's called like Advanced Microcontroller Bus Architecture. It's about 100 pages long, so feel free to read it if you are interested in, or just like Control F to find the location whenever you run into anything specific, and trying to look at the menu to see what's going on inside of this, bus architecture. Okay, some like useful notations when we talk about APBs. These are a lot of the, I guess, visual representatives of what's going on inside of like a clock cycle on each of the signal lines or data lines. And let's first, all those gray areas inside of here basically means we're not sure what's going on stage. It's kind of typical for hardware. Like it takes some time for the hardware to get to where it's supposed to be, like the stable states. So that's what's indicated for that. You don't have to be too, just put some of the gray area there. Make sure they're there and also not too long, because they usually take much less than a clock cycle to finish, much less than a clock cycle. And so from top to bottom, basically we have like clock signal. Those are usually pretty sharp, crisp. We don't have to do any of the gray area to it. And then we have the high to low, like basically digital high to low changes in the signal line. And then, a few other things too. A few things that's being, like the bus stable, you will see like 2 lines. So basically, it doesn't necessarily tell you if it's high or low. That basically means the state where the signal on a bus have reached to a valid, unchanged stage. So that does not necessarily tell you if it's high or low, but it's just tell you that bus is at a stable stage. Usually happens when things just start coming in from the previous instruction. That's where things are stable from the previous instructions, for example. And yeah, bus changes, and then the high Z's that we mentioned is basically mentioned on 2 of the notations. It's where that peripherals or that signal essentially be electrically disconnected from the rest of the circuit. And yeah, some of the bus signals, when we draw them out, and we have, so the APB uses a small set of the signal for communicating between the bus masters as well as to the peripheral slaves. For example, the P clock or peripheral clock, it's basically, it's like an input to the slave device, and then clock signal is for synchronizing the communications across different peripherals and to the core as well. That was connected to all the peripherals. And then we have the P address. It's also input to slave, and it's like address buses that's transferring the address where the command should go into, like a load or store. And that is also connected to all peripherals. So all the peripherals are seeing that the address at the same time. And the P write and the P write data. So also input for the slave. It's the first is the like the write control signal. It's the P write. It's a 1 bit. It tells you whether it's a write or read command, and store or load. And then the P write data is actually the data that's the data bus that carries data from the master to the slave. And that one have like 32-bit as we introduced so far. Yes. Yeah, the gray area basically means that it's the hardware trying to, when the hardware change state, like for example, you have like a switch goes up, or like there is a small amount of time where the hardware needs to be stabilized. Those are essentially what this refers to. Yeah, this is, I think even on this graph, the amount of the gray space is quite like a little bit extravagant. It's usually much shorter than that, but it's just something it's worth to have on the graph. And they are, I think, actually a lot of people trying to just optimize on that, on like material levels or on the transistor levels to improve that in order to do like faster clock cycles. There's also like the P ready. Okay, sorry. It's not labeled on it, but basically it's like a signal that from the peripherals, the slave, that tells it to if the peripheral is ready to react to your command or instruction. And that one, P ready, is connected individually to each of the peripheral. Yeah. Are there always 2 wires to a signal? What do you mean on that? Oh, these, like the parallel going? Yeah, so that's a very good point. So basically, if you go to our annotation, that means it was stable before. So it doesn't necessarily mean if it's high or low, but that just means that was kind of like whatever was before that's been carried over to here. Nothing was changing. It's like a stable stage. Yeah, and just to make things a little bit more complicated, we have a few others as well, like the p-select. It's also input to the slave. It's the select signal, I think you guys mentioned before, for each of the peripheral. It's active high, and this is individually connected. So each of the completer or slave has its own p-select. And we have the p-enable. It's also input to the slave. It's like the enable signal indicate the start of a data phase. It's high during the entire transaction. That one, I believe, it's shared with all the peripherals so that everyone knows something is happening and do not interfere. The p-ready was like we talked before. So each of the completer or each of the slave have its own p-ready stage, so that it knows the slave is ready to do the transaction or to do the instruction that's needed. Yeah.
So for p-ready, so you can go from the stable state to high to ready?
It means it's ready to do something. Yeah. So it's usually, yes. So it can happen. So as long as there's nothing else going on, you can always put that high. You can think of it like that. Like as long as there's no other operations happening on that peripherals, you can just put that high, and then whenever you finishes it, you just you put it back.
What is the relationship between p address and p write address? Looks the same on the.
Wait, the difference between p address and what? Oh yes, the signal looks the same because they are both 32-bit. And the data is the actual data that's being, you need to put into your address or put into the peripherals. The address is where to put into your peripherals. Remember, like the whole system is like a memory mapped in and out. So that was shared between all peripherals to make sure the correct peripherals address have the right signal. Yes? Why would p-ready change? So for example, if there are two sets of instructions or two sets of commands calling the same slave, and then if it basically you should make sure the peripheral is not busying with anything. It could mean a lot of things, right? For example, if it's connected, or if it is doing some previous things that but haven't been able to finish. So usually when you solve usually you put it high as long as there's nothing going on and it's correctly connected. So yeah. So yeah, and this is like a quick example on what's been happening basically. We'll see that at the T0, which is what happens when things coming in, and at the T1, this instruction starts to happen. And you will see that the P write becomes 1. That means the data is being transferring into the peripheral, and you will which is telling that it's a write command or it's like a store command. And then that's when the data started coming in as well. But since it happens after, the clock is always like positive edge triggered. You guys, okay. So although those signals became high, but the actual peripheral or actual system has not noticed that. It will take the next positive edge, basically the T2, so that it knows those signals being updated. And then after that, the P-ready ping is up. So in this case, and that happens after the T2 positive edge. So at the beginning of the T3, the clock cycle 3, that's when everything's ready, and then that's what happened, the actual write. Yes?
Is each signal a different wire?
Oh, which one?
Is each signal a different wire?
Yes, so there are actually more than one wires. For example, the P-ready, for example, like the P-select, it's pretty much one wire, it's on and off, and P-write is also just one. But for the P-address and P-data, it's like 32 wires. That's be connected to everything, essentially. A few slides later, I will show a little bit notation on how those, like a slightly easier way to draw this, but basically, yeah. Some of them are one wire, some of them are more wires. And you will notice that sometimes when it does, for example, like here, like when it does, a little bit cross and the whole thing, that usually means there are like multiple wires. So it's very hard to just represent if it's high or it's low in that whole stage. But for those just have one wires, for example, like the P-select, it starts with low and then become high, and then so you can kind of tell from that how many wires it is in there. So yeah, we talked about this. So what happened? That was like a slightly easier version. So basically, we have like one requester and one completer. What happened if we have like multiple completers or multiple slaves to do? So let's start with P-data. As we talked before, P-data ping was shared to all the peripherals. All of them see the same amount of data, and the trick is when it's your turn to respond. The P-write and P-enable, it's also connected to all the peripherals. The P-write, as the name indicates, tells if it's a read or write command. This is to all the peripherals. And the P-enable is connected to all, and it serves as like a global signal that indicates the start of a data transfer phase. We connect this to all the peripherals so that every peripherals are kind of like synchronized with the same data phase stage, so that there is no collisions. It's easier for the masters to control the data flow. And of course, the address goes everywhere. All the peripherals have the same access to the address, so that they know if it's their turn to be caught up. P-ready, it's an individual signal that for each of the peripheral connects it to the bus. It basically indicates, as we said before, whether it's ready to complete the current transaction, if there's anything else that's holding it. And then the P-clock connects to everything. And a little bit different, so there's an additional thing that they have the completer, like at the end, if it's doing like a, like basically the outside of the output of the data, the 32-bit bus goes back to the peripheral, and it's being assigned as one individual bus structure or like registers there. So this is basically, this means that this is because a lot of these peripherals, the interactions happens at different time. So some of them take longer time to be able to respond. Some of them take longer to get the data. So they do these so that multiple data can be stored correctly there and then being used whenever that's being needed, instead of they might have some like data collision, etc. So basically, imagine you have a set of different devices connected to a system, and then you, for example, flick on a switch on one of them and press two buttons on the other two. All those data essentially are stored separately, so that the processor would know what to do at each of the given stage. So all those signals being preserved individually, instead of just have then connect to one register and then handle all that. Okay. No questions so far, right? Any questions? Yes.
So P-ready is about one wire for each?
Yes, P-ready is one wire for each of the peripheral.
When you have wires,
that basically means the two straight lines means that's the previous stable stage. So whatever it was before, it carries to, yeah. Okay, let's move on. I'm doing great on time. Nice. So now that let's assume just another example, but instead of doing like the whole figure thing, we do a bit more on the actual the actual address and values. So assume we have like one this requester and the two completer device, D1 and D2, and the D1 is mapped to the address from 1000 to 1000F, and the other mapped to 1010 and then 101F. And we have the command, or we have the instruction as store R0, R1 plus 4 after immediate plus 4. And this is what's the course perspective from what we learned from previous lectures. So we will look at the value in the register 1, and then immediately add 4 without updating what's in the register 1, and put that value in the register 0, store the value in the register 0 to that address, right? That was pretty clean from the course perspective. So what does it mean from the peripheral perspective if that one is, in this case, actually allocated or stored into or writes into this peripheral device? I'll ask you to work together on this one, or think together on this one. So these are all the signals that we briefly mentioned, and then can you just think what those signals might look like? Yeah, take some time, don't worry about it, and then we will go through it together. And these are some of the notations on what the, what are those lines mean. But what you keep in mind is that, make sure you notice which of the pings, which of the signals are shared across all devices, and which of these data are individually assigned, and how they would change, around the time. Okay, yeah, talk to your neighbors.
Yeah, but I don't
That could change. We're getting more or after. Yeah, so what was that? Double line. Oh, wait, no. I feel like you need most of them. Oh, wait, like, is T0 to T1 in first cycle? The lower is before the unstable or? Yeah, the lower one.
All right. Any of the thoughts? So, okay, let's get back to the problem here. So we now have the instruction coming in. Let's look at the D1 first, the device 1 first. What happened to the so the T0, the 0 cycle basically is whatever carries over from previous one, and what happened at the cycle 1 here? What happened to the P address? Any thoughts? Okay, give you a hint. So the address got loaded. That's the easier one. So what happened to the P write? Yes. Exactly, it becomes higher, the same cycle. And remember, like that became valid or being notified by all the other system, all the other peripherals after the cycle, the second cycle, positive. This is basically what's the executing cycle. This is after the first T1, like the cycle positive edge, things start to moving, and then within that time, the address got loaded, the P write flag got raised. What about P select for D1? Yeah.
How come it's
The T0 is just carried over from the previous one. So we reduce everything started from the T1. Yeah.
why is it not that?
That's a very good question. We'll see why it stopped at the T3. So the short answer is all these data will be, they stay there for the amount of time they need to stay there. So my wild guess would be after that, this whole operation stopped. But you will see exactly why it stopped at the 3, just in a few slides. Okay, so what happened to the P select on the D1? Are we writing to D1 or D2? D1, right? D2? Okay, we're writing to D1. So that one also goes up. What about enable? There's a little trick here. Yes?
Wouldn't it still be D1? It would just be like high. Well, it would like start off as low, and then it would go high around the same time that the address and D right are up.
For the enable?
Yeah.
Very close. It's actually one cycle after. So that's basically one after the data was updated, already in the process, and then that's when you turn on the enable, so that it's actually in the data phase, so to speak. Yeah. Sorry, what?
What signal does P enable check?
It doesn't necessarily check anything. It's a signal that's assigned by the core or by the core. Basically, it's where, because all the data are ready, so it enables all the peripherals to do the next, or like it tells all the peripherals that there's something going on in the bus. So stay alert. We're actively doing something.
Also, the core enable after it sees that the address changed.
The what? Sorry.
So the core turns on P enable after it sees that the address changed.
It's being handled internally, but basically with all, it's like there's things going on in the whole peripheral bus. Everyone stay alert that we're doing something, doing some transferring. So if you have other things need to dump into the bus, don't. Just wait until it's your turn. And for the write data, they come in at the same time as the address, as you probably guessed. And what about P-ready? Which cycle you think that means it's ready? Yeah. That is correct. So the P-ready is there. You will see some other cases where if you're trying to load something from the peripherals, that signal usually turns on much earlier because it's kind of like ready anytime there's input there. So for this case, it's same time as the enable. So what about D2? What happened to the address? Remember they share the same address, right? So it's pretty much the same as the D1. And for the write, is that shared or individually assigned? The write signal. Like if it's write or read, is it? Yeah. It's actually shared between all the peripherals. We will be using like the select pins and others, which come up to this. So select pin actually is individually assigned. So for this one, it's never being selected. So it stays at low. Yeah.
So did all of them receive a write because it was a store instruction? And in the same way that they all received the same address?
Exactly.
The same, okay.
Exactly. Yeah. Yeah. And then the enable is also a pin that connects to everyone. The data, same here, connects to everyone. And the P-ready just doesn't care, practically doesn't care. It's whatever comes in, it became out. And all these highlighted ones are individually assigned to each of the completers or slaves. Okay, let's see if we can get this as well. So if say we control an LED with the least significant bit of a register, we just how are we gonna do this? So we have to have some way to tell the peripherals to get ready, right? At least we will need the select pins and the enable and the write. They are internally going through an AND gate that only if all three of them are true, this register is being enabled. So those are three different signals that are going inside of the peripheral bus. But but one that actually connects to the registers, because there is only one enable on the register. They kind of doing like a logic AND here. So this register only got activated or enabled if all those are true. It saves space and everything. And all the data, the 32-bit data line goes to the data line of the register. That was pretty straightforward. And then this is the output of the register on the right. So, this says like DQ is basically D flip-flops, 32 of them on one side, 32 of them on the other side. And then DAO is outputting only one bit of the output, which is the index 0, which is D significant bit. And then that turns on and off the LED in this case. And as you imagine, like the clock goes to the clock, which goes to all the registers as well. And in this case, we just have the P-ready connects to what we call like a VDD or logic 1, because it's essentially always ready. It's whenever there's a signal coming in, we just update it as the signal is ready. It's slightly from the before, but that's also pretty common inside of a lot of the peripherals. Yeah. P-ready is basically tells this peripheral, this slave is ready to do the operation that's being needed. It's not like the trigger, it's one of the trigger. It has to be able to do the instructions, but it's not like the only trigger. You also need like select and also enable from like a higher level. Pretty much from, it's an output from the slave to the, it's the other ones are from the master to slave, essentially.
Why is this always ready, but the previous one is only ready at a certain time?
For this one specifically, because we basically we were trying to update as soon as possible. The previous ones, I think it should be okay to have the ready on earlier, but we just want to make sure, because it's a store, we want to make sure all the data and all the other instructions are ready there. And then it turns on the ready. But even the previous one, if we shifted before, because of the enable pin was not on universally, that would not do anything until the enable pin was on. So a few safety nets here, just in case something messed up. And multiple registers in one peripheral, as it's similar to before. We have like all three of them connected, selected, enable, and then they connected to, can you hear me? Sorry. They connected to the enable pin individually on two of them. And you will have the address also being part of the selecting part, because you have to have the right address to know which, in this case, these registers are active. So they all go through a bunch of like AND gates and then determine whether this register needs to be enabled. Yeah.
Why is it only one bit that goes through?
Which one? Oh.
Why is address different, but only one for types of the...
Yes. So in this case, it's the each bit that's directly masked onto one register, so that essentially they connect to 8 of them, and then each one corresponding to 1. Yeah. Sorry, I should. Mm-hmm. Oh yeah, they're missed it. Yeah, we will make it a little bit simpler. In the end, you don't have to draw all these little circles, and we will still recognize it as an AND gate. So yeah, the clock basically goes. The data goes to both of them. Clock goes to everywhere, and data can be clocked in immediately, like before. So we just put the ready to be high all the time. And if it's read, then it's slightly different, as in like each of the completer have its own bus, so we don't have to worry any of the contention on the bus. Remember, like previously, we see all of them have its own register inside of the core. So on that part, it's much easier. Okay, let's get this one through and then call it a day, I guess. So this is a example as a read from a switch, and it's basically figuring out if someone is pushing the switch, and then that would trigger something. So that's whoever that's being on the switch side of pushing. So we will have, again, the address goes to the D flip-flop here, and then the clock goes to clock. P-ready goes to VDD, which is high, because it's always ready. We just want to assume as possible. And that's about it. This is very simple because we're reading from the switch. All the others are not necessarily needed here, but they do come in as the data inside of the data bus. Yeah, but this is how you connect everything. Yeah.
With the enable and the clock is the thing.
The enable and what?
The clock is
That's the clock. No, enable is not to. The clock only connects to the clock. It does not connect to the enable. Enable is the universal signal. It is still connected. So if you look at that more detailed one down there, you will see that enable still goes up after the second clock cycle, and whenever the data is ready. And then the PY goes down because it's a read. That happens just like before in the first cycle. So that's what the diagram should look like. And this is just like a simplified version of the useful components in this particular case. Of course, like the address and select pin, they're all connected. Yeah, just like before. Okay, let me just give one more thing here. It's called meta stability. It happens when